So I think it's time. So welcome everyone. So let's start this afternoon session. So our first speaker is Professor Hanany from the Imperial College London, and he will talk with us about this magnetic quivers, 5D SP SQCD series, the modular space of stress instanton operators. Let's welcome.
Okay, thank you very much. Um, this talk will be devoted to symplectic singularities and the way they appear in supersymmetric gauge theories. Now, there are two known types of constructions. The first one, hyperkähler quotients, or sometimes called Hamiltonian reduction, is known for many years, maybe late 70s, and has been used in various contexts, very well studied construction, and for a long time was a major part of constructing symplectic singularities. Next construction is what I call magnetic construction. Sometimes people call it 3D n equals 4 Coulomb branch, which was actually mentioned in some math presentations a few days ago. This has been very successful, and I still learn new things. I extract new physics from such constructions, so I think we haven't said the last word. And today we will actually be using this construction. Now, for today, I want to promote another idea, and so that's this point of. Let me fix this. The idea will be to have a third construction, which I hope I still don't understand it, so I'll tell you the things I do understand. But I'm very hopeful that with such a third new construction, we will be able to find new symplectic singularities that we couldn't do with the previous two. Okay. So the name of this construction is the space of dressed instanton operators, which is by analogy to what we call the space of dressed monopole operators, the one which is called 3D n equals 4 Coulomb branch. So to understand this notion of dressed instanton operators, we look at 5-dimensional theories, and in a gauge theory, there is a classical object which is called the gauge instanton. It's a codimension 4 object and has a mass which scales like 1 over g squared. And so if I take this quantity to 0, namely I take the infinite coupling, I get new massless objects. And because of that, the Higgs branch of the theory, or the symplectic singularity, is going to become bigger. It's going to change. You start with one symplectic singularity when the value here is non-zero, and you find a new symplectic singularity when the value is 0. So we want to understand this concept. Now, there are several phenomena have been studied for quite some time in the literature. So one is the increase in the Higgs branch dimension. The symplectic singularity becomes bigger. And another one is that there is a symmetry which acts on the symplectic singularity. This becomes potentially bigger. It could stay the same, but it could become bigger. And if we write down the relations, if you look at holomorphic functions on the symplectic singularity, they obey some relations, and those relations are going to be corrected. They're going to be very new relations with the addition of the new objects that become massless. So we want to understand all of those points, and we want to understand how to construct the new space. Okay? Now, the last comment here is that we already know how to take into account all of those points by the use of what is called magnetic quivers. We have techniques that, sorry for that. And so those techniques tell you how to construct a quiver that will characterize the symplectic singularity once when this is finite. So here's an example. Then you construct another quiver which characterizes the symplectic singularity when this value is 0. It's different, it's bigger, so all quantities happen. The Higgs dimension goes up, the global symmetry goes up, and the ring of functions is different. Okay? And so we know this thing. We know it through the notion of magnetic quivers. Can I reproduce it using the notion of dressed instanton operators? This is the question that I would like to address for this discussion. Okay? Any questions so far? Okay, so we will use a notion which is introduced by et Hooft, a disorder operator. So let me remind the ideas behind that. First of all, we start with symmetry, and so there is a symmetry which is natural. Each time you have a gauge group with a non-Billian factor, I can write down a corresponding one form, the one which is here. It is conserved by the Bianchi identity, and so it is topological charge. And with respect to that, I can follow the procedure of et Hooft, introduce a disorder operator, and I won't go over that. I assume that people know this thing. And this actually, he introduces it for a non-supersymmetric theory. And for the supersymmetric theory, I'll assume the existence of operators, holomorphic functions, which carry the charge associated to this thing, and they are chiral. Okay? Any questions about this assumption? So we have instanton operators which show up in the spectrum whenever the gauge coupling goes to infinity. Now, corresponding to this, we can look at the Hilbert space of the theory, or if I think about the symplectic singularity, I look at the set of holomorphic functions. The instanton operator will be acting on a Hilbert space if I start with a state of charge I prime and the instanton operator carries charge I, then I'll get another state of charge I plus I prime. That's the job of such an instanton operator. And for a fixed value of the charge, there's always a minimal one. A minimal in the sense that it has the lowest R charge, cannot be lower than that, and it carries the instanton number, right? Two properties. It may also carry quantum numbers with respect to the flavor symmetry that we have, okay? So those are the three things. And being minimal, I will call it a bare instanton operator. Okay. Now, if I look at the other operators of the same charge, so that I have infinitely many operators of charge I, they will be made out of the bare one plus extra correction factors, which increase the R charge, change the global symmetry, and change the representation under the global symmetry, and these will be called dressing factors, the notion of addressed instanton operators. Now, how I proceed further? So I now give the space of dressed instanton operators. I'm going to figure out what is the bare instanton for a fixed charge I. Since the symmetry is U1, we started with the U1 symmetry, C star. There is infinite of charges from minus infinity to infinity, all integer numbers. And for a fixed charge, I'm going to figure out what is the bare instanton, and I'm going to figure out what are the dressing factors. I collect all of them together, and I'll get the space of dressed instanton operators. Any questions? Okay. So let's proceed. Here's an example. The theory is SP1 theory. I denote SP according to the rank. So the label SP will have the rank. And it couples to a certain number of fundamental hypermagnets. This is the family of theories that we will be looking at. Okay? And how do I get the magnetic quiver? I build it using brain systems. These are examples of tropical curves. Here's the case where this parameter 1 over g squared is non-zero, and here it is 0. Those are the two differences. I have rules for reading the quiver from the tropical curve, and this is what I get. One here, one here. You notice that those are Dinkin diagrams of type affine D, and the corresponding Coulomb branch will be either the minimal nilpotent orbit of D4 for finite coupling, or the minimal nilpotent orbit of D5 for zero inverse coupling. Yes? You could, so we have to make a distinction between a classical instanton solution and an instanton operator. The definitions are different, right? An instanton operator is a disorder operator along at Hooft, and a classical instanton solution is you write down equation of motion. In this case, it's a self-dual Yang-Mills equation, and you look for the classical solution. The self-dual Yang-Mills equation can be read from this brain system. Instanton operator, I have not seen a discussion, but so I reflect the question to the audience. Please construct reliable configurations with brains that represent the instanton operators. Just in order to make a distinction between the different contributions. So here we have 1, 2, 3, 4, and 5, and I have 1, 2, 3, 4, and 5. So the colors just indicate the different nodes that we have. Here you'll have 6 of them, and you'll get 6 different nodes. More questions? So the colors don't mean much, just indicators. Yes? So a tropical curve, in physics we call it the brane web. So those are the 5 branes, the Reshvartz 5 branes, and 7 branes, right? This is a D7, and this is the S dual of a D7. More questions? I will not go over the procedure of taking a gauge theory, constructing a brane system, and extracting the magnetic quiver. This is stuff which was done before, and I'm just going to use results. Okay? So there is a very nice discussion that we can do in looking at how we do all of it. I'm only going to use the results. So let's proceed. I'm going to use another object, and this is an object which is very helpful in understanding this notion of addressed instanton operator. It's going to be a generating function which will have several variables. There will be a variable t, and it's going to be a fugacity for the SU2R charge. Any symplectic singularity has a C star action, which is related to the torus of SU2R. And the power of T will denote the highest weight of the representation under this SU2R, okay? Or the grading under the C star action of the corresponding holomorphic function, okay? Then I'll have other parameters, mu, which will be highest weights for fugacities for highest weights of the global symmetry. Given theories that we will have, they will have quite a high global symmetry, and I want to keep track of the labels of highest weights. I'm not going to worry about the different weights of a given representation. I'm only going to look for highest weights, okay? So if I see a monomial of this type with numbers n, then this corresponds to a highest weight of this type, and lambda are the fundamental weights of the corresponding algebra. For our talk today, we will have the D-type algebra, and we will have, for SON, n different fundamental weights, and we will see how those mu's show up. Any questions? Okay, so let's take an example. The example we saw, SP1 with 4 copies, and we want to see how the minimal nilpotent orbit of SO8 becomes the minimal nilpotent orbit of SO10 when I tune the inverse coupling from finite to 0, okay? So what I do is I take this function. This function represents all possible holomorphic functions of the minimal nilpotent orbit of SO10. How should I read this thing? Mu2 is the fugacity for the adjoint representation. So I should think about the antisymmetric matrices 10 by 10. And statistic exponential is just making it a rational function. So I have a geometric series, and it will give me infinitely many powers of t and mu. And it will tell me that at representation spin 1 under SU2R, I'll have the adjoint. Spin 2 under SU2R, I will have the twice the adjoint, namely that the highest weight is equal to twice the highest weight of the adjoint, and so on. Right? I'll have at the nth order, I'll have the nth adjoint representation. So that's this minimal orbit of SO10. Next thing I do is to decompose the adjoint representation of SO10 into contributions of SO8. So here's a simple decomposition. The adjoint goes to adjoint plus one spino plus another spino plus a trivial representation. And those have physical interpretations. In the theory that I start, I'll have a classical meson. There will be 28 of them. I'll have 2 instanton operators which become massless when the the theory goes to infinite coupling. And I have this one contribution, which is the gaugino bilinear. That's the super partner of the current that we saw at the beginning. Okay. Now it turns out that this the composition here is good for infinitely many contributions. So if I expand this function here in powers of t, I'll get the composition of the adjoint, the second adjoint, the third adjoint, and so on. Okay. From this, I can read that the Bell-Instanton operator at charge I transforms in this representation of SO8. That's a non-trivial point. Any question about anything I said, and particularly the last one? Right, so I have a very high degeneracy of the Bell-Instanton. There are plenty of operators corresponding to the dimension of this representation. This representation has a very large growth in dimension. And it means that the instanton operator has many partners corresponding to zero modes that live in the background of instanton of charge I. Okay? Any questions? Okay. So we finished with the discussion. I gave an idea of what would be the bare instanton. And now I want to continue with the line of reasoning. Let me say a few words about magnetic constructions. So magnetic constructions are good for theories in 3, 4, 5, and 6 dimensions, 8 supercharges. They are called, in some talks, they are called, some papers, 3D and quad-4 theories. And we use them as magnetic quivers for constructing Higgs punches, which do not admit hyperkähler quotient construction. Now, how do we do that? We use the so-called monopole formula. This is the work from 2013 with Zaffaroni and Cremonesi. What we did there was to define a function which is called the monopole formula. And this function computes the Hilbert series for the corresponding symplectic singularity. So it counts holomorphic functions on this symplectic singularity, and it gives you characterization in terms of the representations under the global symmetry of those holomorphic functions. Now, one besides changing completely my line of research, it had quite some nice consequences. First of all, from that point onwards, we were able to compute a whole host of symplectic singularities. We were able to generate new ones and to open a very intensive communication with the people in representation theory, which are interested in symplectic singularity, just because we were able to construct those on an industrial scale. We convinced mathematicians to study such construction. This is known under the name of BFET. And then from the physics perspective, it allowed us to solve many problems where Higgs functions that show up at infinite coupling and Lagrangian techniques are not available anymore. Okay, and it just goes on. I mean, more and more results along this way. Okay, how does it go, this formula? So what I need, if I get a gauge group given by Quiver, let's say, it has a weight lattice. The dimension of this weight lattice is the rank of the gauge group. There is a dual weight lattice parameterized by co-weights of the same dimension. And for each point on this lattice, I have a monopole operator. This would be the bare monopole operator. On top of this bare monopole operator, there are dressing factors. And together, to construct the singularity, what I need to do is to collect all of the bare monopoles, all of the dressing factors. Dressing factors depends on which magnetic charge I deal with. And I sum all of this stuff, and I get the space of dress monopole operators. Okay? Now let's compare this construction with the notion of dressed instanton operators. And note that there is one operator. Do I write it here? Maybe it's in the next one. So there's one monopole operator, one bare operator per point in the co-weight lattice. Okay, very different for the notion of instantons. Instantons have a very high degeneracy, whereas monopoles have a unique ground state. No degeneracy. The dressing factors summarize to just computing invariance of a single adjoint. This is a result from the turn of the 20th century. And the bottom line is that what we have is that half of the dimension of the moduli space is given by bare monopoles, because I have many of them, as many as the rank of the gauge group. So infinitely many of dimension R. And then the dressing factors, because they are invariants of an adjoint. The invariants of an adjoint are given by Casimir invariants. There are R of them. And so again, I have half of the moduli space made out by dressing factors. I collect both of these together, and I get the space of dressed monopole operators. Any questions? Let's compare to instantons. So monopoles, no degeneracies. Instantons, full of degeneracy. We just saw that the bare instanton transform in a very high representation of the symmetry group. So it's going to be a spinor representation. Why a spinor? This is actually similar to the way one constructs Ramon ground states in the type 2 string. I have a collection of fermionic zero modes, and their job is to just add degeneracy. I have a fermionic Fock space, and they give me the degeneracy in some antisymmetric representation, which could either be a baryon, or looks like baryon, or a spinor of some rotation. Okay? And here's how many bare monopoles you would expect if the charge is large, the instanton charge is large, and the rank of the D-type symmetry is N. And the rest of the states are going to be covered by dressing factors, and we will see explicit expressions for those. Any questions? The charge lattice for instanton is just one copy of the integers, Z, right? Because for a single gauge group, non-abelian gauge group, there's only one U1 symmetry, the instanton charge, and it can admit values from minus infinity to infinity. That's it. That's what makes it much harder to construct the space of dress instanton operators, because I need to deal with only one charge, one topological charge, as opposed to many magnetic charges in the case of dress monopoles. I have no degeneracy for monopole. I have high degeneracy for instantons, and I need to also worry about dressing factors, which we still don't understand. I have partial understanding that I will show in the next slides, but it's far from being the end of the story. They will be the fugacities for the global symmetry that you start with. So you take SPK gauge theory with the n fundamental flavors. The symmetry is SO2n, and I have n fugacities, and the general C will be characterized by weights in this representation. Okay, so here's the family that we are going to study as a case model for trying to construct this. SP theory of rank K coupled to NF copies of hypermultiplets in the fundamental representation. Okay? The magnetic construction of the modular space is going to show over here, this quiver. So 1 going up to 2K, 2K appears with this number of copies, 2 nodes of K, and 1. Notice that this forms the Dynkin diagram of type D, finite D. Okay? So I have to ignore this one. That's the only one which is not part of the Dynkin diagram. The classical moduli space is the closure of the nilpotent orbit of this type of the rotation group. A very well studied and well known set of moduli spaces. Okay, so it is the Higgs branch of this quiver, and it's the Coulomb branch of this quiver. Remember the form of the Dynkin diagram. Let's see what happens when I add this effect of infinite coupling. I don't want to talk about this now. Look what happens to the quiver. Let's start here. Here's the form of the Dynkin diagram of type D. So this line here says that I have nodes that start with 1, 2, and go all the way up to 2K minus 1. Okay? Here's the Dynkin diagram of type D. And what I do is to add 2 contributions over there. The 2 contributions are added on spinor nodes of the Dynkin diagram, which tells me that the new states transform in the spinor representation. This family is of type D odd. D odd has complex spinor representations. So I see that there will be an instanton coupled to one spinor and another instanton coupled to the complex conjugate spin. I should think of it as a quiver with the gauge group K, so UK, or the complexifier. So the none of them are dual Coxeter numbers. Well, they are giving the data of the construction of the nilpotent orbit of the modular space. So take this for example. I have those are not Dynkin labels, but they give me the data for constructing the closure of the nilpotent orbit of this type in SO2n. I want to have a different one. I'll have to change the numbers here. One thing I should say about this is that if you're familiar with the data of nilpotent orbits, there is the data which is called the Dynkin labels of the orbit. So for this specific orbit, the label is 1 at position 2K. So I construct one way to construct the quiver is to say I put framing 1 here, and the rest of the quiver I keep balanced. So this is a balanced quiver with this framing. So that's one convenient way of looking at this. If you're also familiar with the construction of slices in the affine Grassmannian. This is one simple example of this type. Okay, so we could discuss many points about that. Yes. Which one? It's those nilpotent orbits correspond to matrices of rank, which is at most 2K and squared to 0. But if I take 2NF by 2NF matrices and I square them to 0, there is a restriction of the rank, which is at most half of the dimension of the matrix. The condition comes from competition of those two conditions, either 2K or N. More questions? Those are quite technical points. We can discuss many of them. Okay, so this was the explanation on the labels. The labels really give me the data for construction of the symplectic singularity. So here's another case over here. There are two additional nodes and they add to the spinor label. Here's the Dinkin diagram of type D. This time it's D even. And there are two additional legs. D even, the spinor is either real or pseudo-real. So the complex conjugate will be, again, the same representation. So they don't touch the other one. They only touch one of them. Here it's again complex representation, so they touch both. And here it's the even, and so there's an effect on one spinor, but not the other. Okay? Any questions? Using this is the data for constructing the symplectic singularity. I now have a whole machinery for telling precisely what are the properties of these symplectic singularities. Okay, so what I'm going to do now is to take this data to compute the symplectic singularity, to compare it with the nilpotent orbit, and to see what are the extra contributions which make these ingredients space of dress instant operators. Okay. So what do I have here? I want this one first. So here are the results. So these are functions which characterize the representations under which the different objects transform. And you see that I have the fugacity T, which characterize the SU2R charge, or in symplectic singularities, this is called the C star weight. There is a C star action, and these will be the weights. These are the fugacities for highest weights of the rotation groups. And Q here is the fugacity for the instanton number. Okay. So I'm going to take this function and expand it. There is a very simple function of Q and Q inverse, so it's very easy to write an expansion in powers of Q, and that's what I get. So let's see what we have. So what we get is that the bare monopole operator, bare instanton operator transforms in this representation and has this R charge. Let's talk about the R charge. A single instanton would carry 0 modes, which make its R charge bigger, and it's equal to precisely the dual Coxeter number. And indeed, for SP of rank K, the dual Coxeter number is equal to K plus 1. So that's the contribution here. If I take instanton of higher charge, It just multiplies this contribution. We didn't expect that this would happen, but this is the result. This is a very nice consequence. And the bare instanton transforms under a single representation. This representation is the ith symmetric power of the spin representation. This example is for odd d, and so the representations are complex. So I have one spinor here and the other. Both of them look very similar, right? It transforms in the ith symmetric representation of the spinor. Single irreducible representation. It's a very simple bare operator. That's one of the surprises. That was one of the excitements that I saw when I had this computation done. Any questions about the bare instanton? So what you do is to compute the dressing factors, and here's a very big surprise. The dressing factor, when written in terms of those functions, does not depend on the charge of the instanton. There is no I dependence here. It's uniform. It's the same dressing factors all over. But the representations are very different, because if I take this label here and add such a label here, I'll get a completely different representation. But when I write it in this particular way, I get this beautiful result that the dressing factors are independent of the instanton number. Okay? That's the reason for the excitement. And you just repeat the story for all of the cases, and this is the table, bare instanton, dressing factors. So now I have the picture. I need to collect all of those together. I have all of the bare instantons, I have all of the dressing factors, I collect them together, and I get the functions that I got from the, not this one, explicit computations using the Quivers that we showed. This is the result for infinite value. Okay? Any questions? So here's the fugacity for the instanton. This is the negative. So this is the even case, therefore they couple to the same spinor. And that's the odd case, so I have positive charge for this spinor and negative charge for the other spinor. Yes, yes. That's the, I mean, it's all very beautifully matching. I have a very nice picture of the all possible bare monopoles, the degeneracies, and the dressing factors, which are actually independent of the instanton number. So it's just one dressing factor. Which dual picture? Oh, it's a 5-dimensional theory. I don't say anything about the Coulomb branch of the 5-dimensional theory. And the magnetic quivers have one purpose for me. Their job is to compute the properties of the symplectic singularities which show up when I tune the gauge coupling to infinity. Right? So it's a new construction. So it's, well, not new. It's a magnetic construction for a symplectic singularity that I will not be able to get using Hamiltonian reduction or hypercurrent quotient. That's the only way I know how to construct those symplectic singularities. And with this data of the quiver, I can compute any property that I wish to check with respect to this singularity. More questions? So let's summarize. In total, what we saw is that, first of all, I can use the technology of magnetic quivers in order to construct the symplectic singularity which shows up at infinite coupling. Already this is a non-trivial point because it solves a problem that was present for maybe 20 years, 25 years. We knew that the Higgs punch changes, but we didn't know precisely how, what precise way they are. And all of the data is encoded in terms of those magnetic quivers. We also saw that this way of representing the data of the holomorphic functions, in physics language, the chiral ring, all of the data of the chiral ring is stored in those generating functions, which we saw here, for example, right? So let me just emphasize, these are rational functions, simple rational functions, and they, when I expand in powers of t, so that's in powers of the charge under SU2R, I get infinitely many contributions, but it gives me the precise spectrum of half BPS operators, all of the protected operators of half a BPS. Okay, I can tell what is the R charge under SU2, and I can tell in which precise representations they transform. Representation of the global symmetry. Okay, if there is an enhancement of the symmetry, it shows up in the function here. And then using those generating functions, this was the way to come up with Baire operators with dressing factors which are independent of the instanton number. And yes, without brane systems, I show it briefly. Given a brane system, that's the way I use to compute the magnetic quivers, and from the magnetic quivers, I extract the data of the symplectic singularity. So this is a very important ingredient. And finally, the monopole formula. This is the thing which started all of this analysis. It's without it, I wouldn't be here to tell you all of those nice developments. Thank you very much.
So thank you, Professor, for the very nice talk. So are there any questions?
So if I take, let me show an example. Let's take minimal orbit of SO2n. And so this will be the Higgs branch of the quiver SP of rank 1 with SO2n. This is a Crab-Pochesi quiver. And the generating function, the highest rate, I'll denote it like that, is PE of mu2 p squared. So this takes the form 1/1 minus mu2 p squared. And now I can expand it. this is the weight of the sister action of the symplectic singularity. So if I look at C star, it's called the, what's the way you call it? The degree, or say? Yeah, I mean the weight under the C star action, and this is going to be the representation, a unique representation under which the holomorphic functions transform. So for SO8, I will get 1 plus 28 squared plus 304, and then there will be no contributions. So this is the weight of the sister action, and this is the notation for the adjoint representation. So this is the first adjoint, this is the second adjoint, and so on. I hope I answered the question, if I understood. Sister action of the so if I have, let's say, a Poisson bracket, I have to function. The third function, this will be having weight A, this will be B, this will have A plus B minus 2.
So are there any other questions?
Maybe I don't use it. The way we constructed it was just to along the lines that I described. But I just enumerate all possible bare monopole operators, and I just take into account all of the possible dressing factors per monopole operator, and the monopole formula just sums all of those contributions. Now there were later developments, but we still use this thing. You know, if you look, for example, at the construction of the mathematicians, BFN, it's called. 5D. Could be, except that in general, I think we were, so this property of having a dressing factor, which is independent of the instant on charge, to me looks like a nice accident. I don't have any justification for doing that. That's the reason also for many years I haven't tried. But when I saw that there is independence, I said, okay, that's great. Now I have a way, for at least for a two-parameter family, I can construct the space of dressed instant-on operator. I can start from minimal SO8 and I get minimal SO10, just like that. It's let's look at the cases. So magnetic quiver is nice because the data of the dimension is just in front of you, which is another possible answer to Sergio. So the dimension of the Higgs branch is just the sum of the labels minus 1, because there is an overall 1 which acts trivially. So you just sum those numbers and subtract 1. Now, let's take this thing here, right? So I can compute, I just sum. Let's compare it to the case without. This one, that's the case without. I can compute the sum, subtract 1, and get the dimension. And the difference will be the increase. So we should have a table. Actually, sorry, I did not provide. There'll be a nice table which will tell you the increase in dimension as a function of those two parameters, k and n, which will tell you the increase. It's not a simple dependence, because you could see that the behavior of the quivers is changing each time I change the number of colors and the number of lengths. Right, so it's given here.
Okay. So more questions? So if there are no more questions, let's thank the speaker.